Hello boys and girls. This video is a kind of add-on to the previous video where I explained how to use hash functions in the new smart contract framework, and we're going to take a look at a little bit more technical details and requirements for good hash functions and how things look under the hood. But before we go into that, I want to start a little bit softer, and I cooked up a procedure that is, I guess, a kind of hash, except it's not a good hash at all regarding what you want from a hash function. But this is a kind of procedure which is easy to explain and has some crucial similarities, and I want to go through that before we deal with the bits and bytes of how things are actually implemented. So what we want to do here is we want to take some string, let's say it's a password, and map it to another kind of randomized looking string of a fixed length. And what I was thinking is that we do the following. So we are only going to deal with the characters from A to Z here, and what I did here is I split them into two sets. So you have your A, B, C, D, E, F and so on. So these are all the characters in the alphabet, and we have all the uneven characters if you enumerate the alphabet, and here are all the even, so B, D, F and so on. And what we are going to do is we're going to take any word, let's say the password. Here in this example, let's say it's coin. This is the word that I want to use as an input for the hashing function. We are going to do a padding to guarantee that the input is 8 characters long. So after the word we're going to add A, B, C and whatever, so then we end up with something that is 8 characters long. So for example, if the word is hello that we're going to provide as input, then the word that we start with is hello ABC and so on. And then we have an 8 character word, and then we're going to go through that word from left to right, you know, letter by letter, and dependent on what character we're at, right? So for example, the first one would be a C. Then depending on the row in which this character falls in the split that I did before, I'm going to do some operation to the whole string. And so what I cooked up here as to explain this is the following. If the character should be in the upper row, so if it's A, C, E, and so on, then we're going to switch the character with the character that is 4 characters ahead. So for example, if we are going to switch the third character, so the third character would be an I, the operation would be to take the character that is 4 characters ahead, so there would be the C here, and just switch them around, right? And so if you take the third one and switch it with the character this is 4 ahead, we get another word, and this is like this word, right? You're going to see how this looks in the example when we go through it. And the other operation that can happen is if the character is in the lower row, then what we're going to do is we take the next 4 characters and substitute them with the character that comes after that in the alphabet. So what this means is, if we add 1 to, like if we do the add 1 operation to this second character, so here is an O, then we will take O, I, N and A and add them up in the alphabet. So for the O, after the O in the alphabet comes a P, so O becomes a P, I becomes a J, N becomes an O, and A becomes a B. So you know, you see these 4 characters are raised, and then you get another word, and these words are always gibberish because you did some random switching or addition. But the hash is going to be a kind of play with these kind of operations, and in a hash you do a lot of these operations, like thousands of these operations, and you switch it up and repeat, and that's what we're going to discuss in the second part.
Yeah, because hash functions have some other properties, but those you will see in a second part, and now we have a simple example.
Right.
We'll see how
yeah, so I want to emphasize that this is not a good hash function at all. I can say a word on what's things that are missing at the end. But so in case that was the procedure was a little bit too complicated to follow here, here's an example. So let's see our input word is the word hello. As I said before, we want to have a word that's 8 characters long, so we pad the word, we make it 8 characters long by just adding ABC and so on at the end. So this is basically the start. And now we're going to go through the letters and do the operations depending on whether the character that we are at falls in the first row or second row. So we start with the first character, which is an H, right? So this is in the second row, and we have to apply the add 1 operation to the 4 characters that come after that. So the H becomes an I, because in the alphabet after the H there's an I. The E becomes an F, right? L becomes an M. So these 4 characters, they are all just shifted +1 with respect to the alphabet. Like they become the character that's after that. And so we applied the first operation. Then we get another output word, and we go on with this game. So we go to the second character now. This is an F. It's again in the second row. So the F, the M, and the O, like these 4 characters, they are shifted in the alphabet again. So the I stays the same. The F becomes a G, the M becomes an N, M becomes an N, and O becomes a P. Okay, then we go on, and the third character is now an N. Okay, it happens to be again in the add 1. So the N becomes an O, the N becomes an O, the P becomes a Q, and the A becomes a B. So 3 times this pump function. Then we are in the 4th row, and in the 4th row here, the 4th character is an O, and it happens to be in the 1st row here. So now we're going to do the switch operation, right? And I said in the switch operation, I switch the character with the one that comes after that. So the O is switched with the C. So you see that the O goes there, the C goes there, and we did this operation. And then we go on. The Q happens to be also in the switch part. Okay, 1, 2, 3, and then if we run out of space, we just start at the beginning again. So what I'm going to do is I switch the Q with the I, syrup. So this is the new word. Then in the 6th row there's a B. So now again a pump. So these all are left these are left the same. Then C is +1, C is also +1 from B, P is +1 from O, and then I go back and say the Q is also +1. So I have 4 characters that are raised. With the C, the same thing happens again. C and P are the C is actually in the 1st row, so the C is switched with the O here, so 1, 2, 3, 4, so right, and finally the P is in the 2nd row, so the P becomes a Q, R becomes an S, G becomes an H, C becomes a D. And so what happens, we did 8 operations, and we mapped the word hello to this strange looking string. And now we have basically the operation that we want from hash function. It's not a good hash in many regards, because, for example, you know, I could do it by hand. It's like very simple, and these 8 operations are like computationally simple, and to break the hash, like for example, I could write a computer script that takes this short output as an input and just tries a lot of words, right? It tries hello, it tries tree, it tries mouse, it tries Alexandra, and applies this operation to the word and just tries what comes out. And this is just too simple, and also here, for example, these letters, you see the G's, they appear for a long time always the same, because these operations are so minor that they usually don't change a lot of characters in the word. So there's not enough switching up going on. It's too simple, and it's therefore easy to break for whatever things I want to secure, if it's like a cryptographic hash application at least. It might be that some of these properties are not really relevant, but for cryptography you want to have it basically as complicated as it gets.
Yeah, but the outcome should be very easy to calculate with, and here our outcome was even longer than the input, so that's another thing good hash function wouldn't do.
Yeah.
So now we have a look on another example. We have here the word was.
Yeah, from Wall Street.
And we add the letters A and B, because was is 6 letters long, and we want to have 8 letters. The first is W, so W is in our first row, which means that we have to switch W with the 4th letter, so 1, 2, 3, it's so the others stay the same. But we have to switch the 4th letter. So here we get W. The 1, 2, 3, 4. So here we get the W, and here the S. So now we are at A. A is again in the first row. So again we count 1, 2, 3 and 4. Those stay the same. But A and T are switched. We are at L. And L is in the second row, which means that we have to go a letter up. So L becomes M. And the next 3 letters also get 1 letter up, so L again M. W is X and A to B, and the others stay the same.
And you know, we can continue, but I guess you get the gist of this, and we would apply like 1, 2, 3, 4 more operations, and we would end up with this word. But then you can already see here, for example, the M, like after we go through the M, it doesn't change anymore, and apparently this T is raised once more, and so there's some change going on, but it's a little bit too simple. Like you see traces of this input in the final word. But yeah, I guess you get the idea. Like now you can try to design a good hash function, and you know this has been done for decades to try to find let's say complicated operations. But in the end, it's really just play with the characters. And when I say characters, you know, on the computer, all data, like let's say a string, is really just encoded as zeros and ones. Like this is like an array of bits. And they are grouped together into bytes, which are 8 bits, and so you have to the power of 8 different configurations, and those are then interpreted as numbers. And so in reality, when you implement a hash function on the byte level, you work with long arrays that you can interpret as numbers, and then you can do much more complicated or sensible operations than just raise the letters in the alphabet. You can actually do some arithmetic or whatever complicated operations you want to do, or simple operations, and you can do bitwise operations, right? You can compare different bits, different zeros and ones, and then do some Boolean operations and functions on them. So in the implementation, this will all happen on the bit level, on the byte level, but this is the gist of it. Okay. Okay, so today we have another Alexandra episode, and she will talk about secure hash algorithms, of course.
So thanks to Nikolaj for his introduction. Today we talk about hash algorithms, and here we have an overview of it. Hash algorithms take an input, let's call it X, and generate an output called H from X. And in case of the SHA-1 hash algorithm, this output has the fixed length of 160 bits. So there are some properties that our hash algorithm, like SHA-1, should have. As already said, it should have an output of a fixed length, and this length of the output should be shorter than the length of the input we do the hashing with. That's because we want it to be very easy to do following calculations with this output. But the hash is used to verify that some message is really this message. So there should be no collisions, meaning that if, for example, you want to send a message, X is X1, somewhere is Xi to Xn, and there's an evil person, Oscar, who makes a message X tilde out of X. He changes Xi to X tilde, Xi tilde. Then the hash we get with X, let's say the hash we get from X is some value Z, should be different from the hash we get from X tilde, which is some value Y, and Y different from Z. It's not possible that there are no collisions, because you have much more inputs, because you know they could be of arbitrary length, so you can have much more inputs than outputs. That means that there will always be some different inputs having the same output, so having the same hash. But it should be very, very difficult to calculate a different X tilde that has the same hash as X had. And there's another important property, that's the avalanche effect, meaning that if Oscar, for example, changes only one bit of the message, the change in the output, so you know this is a list of some bits, then in the output there should be a larger change than the change he did on the input, so there should be more bits changed. Now we have a closer look on the SHA-1 function. because it's the most common used hashing function so far. So again we have our input x, x1 to xn, and if this input is smaller than 512 bits, we do some padding, meaning that we add other bits like zeros and ones to generate a message of 512 bits, because that's what we can work with later on. And if the input is longer than 512 bits, we have to make parts out of this input, and the parts that are shorter than 512 bits will be padded on to. And after this padding we have our 512 bits message, and this is put into a compression function, so a procedure that makes only 160 bits out of this 512 bits. Of course there is information lost in shortening this message, but as we said, there should be no collisions, or they should be very difficult to find, and there should be an avalanche effect, so somehow this hash, the h from x, some value, should be an identifier for our message we put into this hashing procedure. And the compression function doesn't only take the input and generates an output, but more times so we take in the 512 bits, and it does something with these 512 bits, so that we get a value only 160 bits now. And this is put into the compression function again and again until our procedure stops and we get the hash we wished for. But how this compression function really works, we will see in another video.
Okay, so now in the second part we take another look at the compression function as part of the hash algorithm in a little bit more detail and technical level. And I want to say that here to do the computation at this is like on a computer level. Okay, so now in the second part we are going to take a closer look at a part of the procedure, namely the compression function. And you know, this involves a lot of computer operations, and in particular also arithmetic computations that, as you saw or in the last video, for example, on the website, really take only fractions of a second, even though there are like hundreds and thousands of operations involved. And I want to emphasize that we can do arithmetic operations here, so operations with numbers, because whatever the data on the computer represents, like for example some random looking strings, under the hood this is really just a series of bits, and they are partitioned into bytes that hold different bits, and you can then take these bytes of some numbers, interpret them just as some numerical values, and then do the arithmetic operations that are used in the algorithm here.
So now we have a look on the compression function, and we had our hi-1, this was the output we saw on the graph before, so it was the output from the last round, and our xi minus xi, which contains of 512 bits. This is the message we got when we finished the padding. So these are 512 bits and these are 160 bits, and our output will be 160 bits again. So we have round 0 to round 79, which are 80 rounds in total. And these 80 rounds are grouped into 4 stages. Each stage contains of 20 rounds. So stage 1 goes from round 0 to round 19, stage 2 from round 20 to round 39, stage 3 from round 40 to 59, and stage 4 from round 60 to 79. And these 4 stages determine how our function ft and our round constant kt do look like. So these two will come into the game in a moment. And so we have 4 different functions, because f1, f2, f3 and f4 for each stage, and also 4 different round constants.
So in these 4 blocks there are 4 items that are used for the computation that mix the bits and bytes together like spaghetti, and they the system is grouped so that they also change, so it gets even more confusing if you want.
So now we have a look on how each of the rounds to look like. We have this 160 bits and we separate it into 5 blocks of 32 bits each. So we have block A, B, C, D and E. And with these 5 blocks we do some simple calculating with. So we take blocks B, C and D and put them into our function, which is determined by the stage.
Right, so to say this again, so we have this input, we partition it into 5 parts, and then we take these parts, and these parts can be taken to represent some numbers, and now we can do some operations with them. These are these boxes here, and so we intermingle the bits and bytes of the whole message together in some fabricated fashion to get some new value out of it. And whatever is the input, you get an output, and if you repeat the process, a lot of things happen here, but you always get the same output.
So if you're wondering what this box does mean, it's addition modulo 2 to the power of 32. And if you're not a mathematician and don't know this, it's some kind of special addition with bits. Here we take our block A and shift it by 5 bits to the left. This means we take the first 5 bits and put it to the end, so bit 6 will be bit 1. And
this is roughly similar to the rotation that we did with the bit cheap hash function that we explained before.
And block B is shifted by 30 bits, and in order to make it a bit more complex, it's not A to block A, but block A becomes block B becomes block C,
right.
and so on.
This is also like just a switch, but on a kind of bigger scale, right? So here you have, within the block there's something shifted, and here in a sense there's also some switching around, right? But this is also just computation in one of the steps here, and within this you have this addition that's like a little bit like the pump, right?
Yeah, and for these additions our words, which are determined by the message schedule, we will discuss in a moment, and our round constants come into the game, and they are only used at this point. So now we will discuss the message schedule. It's very easy, so we just have our 512 bits long message, and we make 15 blocks out of it, each block contains 32 bits. So it's not only partitioning, but it's a bit more complex. So we get 16 blocks, block 0 to block 15, and these 16 blocks become our first 16 words, so word 0 to word 15. And for the last word, so word 16 to word 79, we do some calculating with the first words. It's some kind of special addition again, so we XOR.
So again, some bitwise operation.
Yeah.
We don't explain really these operations, but it's a kind of, you know, like the pump. It just changes the values in on the particular place.
Very easy to calculate, so that this works very fast. And yeah, as we said, in the end we get our 160 bits output, and these are taken into the compression function again. And so because this was our round 0 and round 1 looks the same up to round 79, so we put this outputs into the compression function again and again until we have a final output, and this is our hash.
Okay, thank you.